Visible? The screen is
Yes, sir.
visible?
Yes, sir. Visible. The screen is visible, sir.
So this is about the on-off controller. Now, second one is proportional controller. This is again very simple controller is there. So here, first of all, how to obtain the transfer function, then individually we will discuss their advantage, drawback. So in this case, this round comparator RT reference signal is in RT. It is the error signal, and this is the actuator basically. We have to obtain the transfer function of this actuator, and their output is empty. So now onwards, in all cases, we will discuss as this rectangular block, which is the comparator part of the controller. Basically, if this part is controlled, entire system is going to be controlled there. So basically, instead of considering the controller, we are going to consider actuator as the controller here. So this is the actuator. Their output is empty in time domain. Input is ET, which is the error signal. Accordingly, in the frequency domain, RS, ES, and MS is there. Now, in what basis the name proportional controller is there? So if we consider the relationship between output and input of this controller, that is MT is directly proportional to ET, or MT is equal to some proportionality constant, which is denoted as K, and P for the proportional first letter of P into ET, where Kp is the proportional sensitivity, or it is known as proportional gain. If we take the Laplace transform, then Ms is equal to Kp into Es. So we can find the transfer function, that is the ratio of Laplace transform of output Ms to Laplace transform of input Es with some conditions, then that is equal to Kp. So here the transfer function of this controller, proportional controller, is Kp. This here, how to realize this Kp. So whatever the actual mechanism may be and whatever the form of operating power, basically the proportional controller is essentially an amplifier with an adjustable gain. This amplifier may be an electronic amplifier or a hydraulic amplifier or a pneumatic amplifier. So here output of the P controller varies linearly with this error signal. Then again, one additional term is there. We are familiar with the steady state error. So a steady state error is the difference between the desired value and the actual value in the final state or in the steady state. So general difference is there. Desired minus the actual is known as the error. But when we are considering in the normal state and in the final value, that is known as the steady state. So this is the steady state error. But if this error is because a step input, then this one is known as offset. So industrial people know this difference in terms of the offset. So there is a difference between offset and the steady state error. The steady state error is the general term. It may be because any type of input. But when we are going to consider offset, this offset is a steady state error only because of a step input. So industrial people only knows this one is offset. Now, this is a simple controller is there. So what is the advantage? It is simple and stable, and it can be used alone if certain error is tolerable. Then the disadvantage, it always causes offset. Offset means a steady state error. That means there is a steady state error in the response to a step input. And second drawback is response is very slow. So then how to minimize the offset? Because in the time domain, we know it that a steady state error is equal to 1 by 1 plus Kp. So if we are going to increase the value of Kp, we can minimize the steady state error ESS. Now, when we are going to increase the value of Kp, now our expectation is there, if can we increase Kp up to a very large extent so that the steady state error will become or offset will become 0? That is not possible here. We can increase the value of Kp up to certain level. If we are going to increase this value of Kp beyond that, then the system will become unstable. So that means offset that is the steady state error, cannot be fully eliminated only by using the proportional controller. But if we are going to add along with the proportional the effect of integral, then this can be eliminated. So that will come later on, because the offset here can be eliminated if the integral control action is included in the controller. Now, simple block diagram is there because comparator, then KP is the only the proportional controller is there, GS is the plant, simply GS transfer function we have kept. Later on, we will consider the transfer function for a second order system. Then YS is the output. Then this electronic proportional control, how to realize this controller, proportional controller. Because this is a general principle is there. Suppose here in this case of, we can realize by using the operational amplifier, or here we are only considering here the circuit diagram. Basically, it will be realized by the using the operational amplifiers there. So here K block, which is the amplifier gain. Then output is denoted by T. Input is denoted by EI. And then the two signals here is there, because EI is the input and EF is the feedback signal. So there are difference. EI minus EF is going to become the input of the amplifier. And whatever the output is there, this output is applied to a potentiometer where the total value is R1. And R2 is the variable one because this position is going to be changed. So then we have to consider KP means what? So this diagram is known as the a schematic diagram of an electronic proportional controller, because a scheme is given here. In what way we can realize the element. Now we can see what is the relationship. Output is the E0, which is K into error signal, that is EI minus EF. That is equal to K. EF is equal to R2 by R1 into E0. So if you take the Laplace transform, then E0 is equal to K EIS minus K R2 by R1 ES. And now you separate out and take the ratio E0S by EIS. That is the transfer function. So the transfer function is coming here K by 1 plus K into R2 by R1, where K is the gain of the amplifier and R2 R1 is the position of the potentiometer. Now, since here K into R2 by R1 is very, very larger than 1, so we can neglect 1. Then transfer function is coming as simple way, GS is equal to R1 by R2. And that is nothing but it is the KP. So in what way KP can be realized here? This KP is coming as R1 by R2, which is in our hand. We can change the value of R2. So KP is the gain of the V controller and can be adjusted by changing the ratio of resistance R1 by R2 in the feedback circuit. Now, another one is the operational amplifier diagram. Next, then same proportional controller can be realized. This one was in the electronics way. In the pneumatic way also it is can be applied. So in the case of pneumatic proportional controller, the arrangement is between the flapper and nozzle. This is a major component, flapper and nozzle. So here this is a flapper, and here this one is the airs, because in the case of pneumatic proportional controller, air supply is the source. This part is known as the orifice. So this is the PS is the supply pressure, and PB, that will become a back pressure, and this PB will be larger than the PS. In this way, some concept of amplification is going to be used here. So here this flapper is going to move in a smaller way, because here the condition is nozzle diameter. Here this is the nozzle part is there. Nozzle diameter must be larger than the orifice diameter for the proper functioning of the amplifier. And here low pressure pneumatic controllers are extensively used in the industry process due to explosive proof characteristics. And again, it is very simple and easy to maintain. Now, in this case, nozzle flapper amplifier converts a small changes in the position, because we are going to change the position of the flapper. into a large changes in the back pressure, that is the PB. And thus a large power output can be controlled by very little power that is needed to position the flapper. So here nozzle flapper amplifiers converts displacement, because input is moving the flapper, that is the displacement. So displacement is the input and output is the back pressure. So in this way, the concept of amplification is used. Again, in this case, if we further amplify, then we can use a pneumatic relay, can be implied as a power amplifier in connection with the nozzle flapper amplifier to make it sufficiently large. Now, another controller, integral, because exactly in the same way, one can realize the hydraulic controller in the proportional way. Now, we are considering we have discussed on-off controller, then proportional controller, then integral controller. Integral controller, which is also known as reset control, or you can say integral control action and reset control action. Accordingly, the name is integral controller is there. So again here, this same nomenclature of the signal RT input, ET is the error, MT is the output of, and this part is the actuator. So here the relationship is rate of change of controller output is proportional to the error signal. Means dmt by dt is proportional to ET. And so dmt by dt is equal to k, some proportionality constant. And since the name is integral, so we are using I. So ki into ET. So where ki is known as integral gain, which is adjustable. We can adjust it, adjustable a constant. So from here, we can get the idea mt is equal to ki integration 0 to t et dt, and that's why the name is integral controller. So if we take the Laplace transform, so ms is equal to ki, and this one is es because of integration, that is 1 by s. So transfer function ms by es is equal to ki by s. So in the case of integral one, there is the addition of one pole, k here ki by s. In the proposal, it was only kp constant term, but here it is ki by s. So here the certain features are there. If the value of ET means error signal is doubled, then the value of MT means output varies twice as fast. Then for zero actuating error, the value of MT remains stationary. And offset in this case of P controller can be eliminated if the integral control action is included. Then the control signal MT can have non-zero value when the error signal ET is 0. Whereas in the case of proportional controller, a non-zero constant signal requires a non-zero error signal. So advantage of this one is there. A major advantage, it eliminates or minimizes the offset which was there in the case of proportional controller. But this one having the major drawback. So disadvantages, introduces hunting in the system response about its steady state condition. So what is the meaning of hunting? Hunting means around the steady state, the output is going to search the final value. Means it is moving up and down around the steady state value, but it is not getting the final value. So this is known as hunting. So this is the major drawback of this. Integral control action has destabilizing effect on the process under the conditions of, again, load variation. So these are the drawback. Again, this one is if we are going to realize by using the operational amplifier, and in detail we have not discussed here, one can obtain it. Then another type is derivative controller, which is also known as rate control, derivative or rate control. So here the relationship is there. Output MT of the controller is proportional to the rate of change of error signal. Means MT is proportional to DET by DT, or MT is equal to some proportionality constant, which is known as here KD, DET by DT, where KD is the derivative gain. So if you take the Laplace transform and take the ratio, so transfer function is equal to MS by ES, that is equal to S into KD. So again, S term is here in the numerator, means a 0 is added here. So if we consider The features, it gives a rapid response to counter the effect of rapidly changing error, but it is ineffective for slow changing, and hence it causes a drift, that is a flow. So it operates on the rate of change of error. Now, if you consider the advantages of the derivative, it has an anticipatory characteristics. It can identify the error in advance, and accordingly it can take the action. It increases the stability of the system, fast and transient response. Derivative control adds damping to the system and thus permits the use of a larger value of gain, which will result in improvement of the steady state, not directly, but this is the indirect effect is there. So disadvantage, this is the have a major disadvantage. It picks up noise, means unwanted signal, and amplified. As a result, the system becomes unstable and it is going to damage the entire system. And again, the second major drawback is there, it doesn't care for offset in a direct way. So if we are considered out of three individual controllers, P controllers, D controllers, and I controller. P controllers can be used alone because that is the simple and it can be realized by using a amplifier. I controller cannot be used alone because output is not going to become a stable, which is known as hunting, because around the steady state it is going to move upward and downward, but it never reaches the final value. Because of that, I is not used alone. And derivative, the major drawback is there, the response will become divergent. As a result, it will damage the system. Again, derivative is not used alone. So out of three individual, only proportional is used alone. Now we have to think the combinations of the proportional plus integral, proportional plus derivative, not combination like derivative by integral, because derivative is not used alone, integral is not used alone. So it can be used only with the proportional. So here the another controller is proportional plus integral controller. So again, we have to obtain the transfer function of PI controller. So here the relationship is there, MT is Kp into Et plus Kp by Ti and integration Et dt. And if you take the Laplace transform, then Ms is equal to Kp Es plus Kp by S Ti Es. So you can obtain the transfer function. So transfer function is coming as Kp within bracket 1 plus 1 by Ts, or you can simplify it, where Kp is the proportional gain or proportional sensitivity, Ti is the integral time, and both are variable. Kp and Ti both are adjustable. Both can be adjusted. Now, what is the integral time adjust? Here, the two parameters are there. One is the integral time, other is the Kp proportional gain. Here, integral time adjusts the integral control action, while change in Kp affects both proportional and integral part of the control action. And here, Kp by Ti, that is known as the Ki, that is known as the integral sensitivity or integral gain. So here again another word is used, that is known as the reset rate, just like offset in the proportional. So again in this case of, because accordingly the name is reset control. So what is reset rate? It is the inverse of the integral time. Inverse of the integral time, that is 1 by Ti, is known as the reset rate. Or the reset rate is the number of times per minute that the proportional part of the control action is duplicated. So reset rate is measured in terms of repeats per minute. If we consider the characteristics here, the input applied is a step input. So you need a step, that is the ET. And if you consider the response here, so response, this part is because of the proportional only. And because of combinations, the response is coming like this one, because the integral action. Integral action, this is the ramp response is there. So this is the proportional control action is there. And accordingly, we can find the parameter, that is the integral time, Ti. Then what is the schematic diagram here? A schematic diagram of Pi, how to realize here. So here comparator, then Kp, proportional, and Ki by S, that is the integral part. These two signals are added, and then this is given to the plant, where plant is described by omega, general standard plant, omega n square by S into S plus twice zeta omega 1, where zeta is the damping. So, and because unity feedback is used here, so if you are going to obtain the loop transfer function, GSHS, so GSHS is 1 and combined part. This combined is considered as the GS. So this one is simplified because these two are added, Kp plus Ki by S into omega n square divided by S into S plus twice zeta omega. You can simplify it. And then you can obtain the final Ys by Rs. So finally, you can see the nature here. That is simply GS divided by 1 plus GSHS. So GSHS is known to you, you can simplify it. So then this one is coming like this one. So here we can see what was the order of the plant. Order of the plant was 2. Now because of the integral one, the order is going to increase. So here, since the order of the system increases, the system is susceptible from the stability point of view. Hence, because order from second to it has become the third order, hence K should be designed properly to make the system stable. If you are going to consider the steady state error for a ramp input here, this is a 1 by kV, and because here kV is equal to limit S tends to 0, S into GSHS, and that becomes infinity. So a steady state error is going to become 0. Means if we are going to apply ramp input, then the steady state error will become 0 here. So system behavior is going to become accurate due to reduction in the steady state error. So what are the main features of this PI controller? So in the case of PI controller, order and type of the system is increased by 1. Order is also increased, type is also increased by 1 because Ki by S is added here. So that is the number of pole at the origin is the type of the system. So this addition is there and order is second to third. So order and type of the system is increased. As a result, a steady state error decreases. So that may be considered as advantage here. Improvement of damping and reduction in the overshoot. Damping is going to be improved and again overshoot is going to be reduced. That is also the advantage here. Bandwidth also increases. Noise is filtered out, but Ki must be designed properly. So care has to be taken here. So advantage is a steady state error decreases. So when we are going to use the PI controller, the major advantage is there, the steady state error is going to be eliminated. That is the major advantage. And drawback, since the overall gain is going to increase, again, order of the system is going to increase, hence the chances the system will become unstable. So that's it. Overall, the system will become less stable. So this is the major drawback. Again, proportional control action tends to stabilize the system. If we are combining summary point, so proportional controller tends to stabilize the system, while the integral control action tends to eliminate or reduce the steady state error in the response to the various inputs. Now, if you are simplifying, then you will find there is a 0 at S is equal to minus Ki by Kp and a pole at S is equal to 0. Then in the form of operational amplifier, this realization is there. Then proportional plus derivative controller, PD controllers. So in this case, this is also known as rate control because derivative is known as the rate control because their output is proportional to the rate of change of error. So that's why this is also known as a rate controller. So in this case, this relationship is defined like MT is equal to KPET plus KPTD DET by DT, where if you take the Laplace transform, so MS is equal to this much, and if you obtain the transfer function, then transfer function is coming as Kp plus Kp TdS, where Kp is the proportional sensitivity, proportional gain, Td is the derivative time, and product of Kp and Td is known as Kd, that is the derivative gain. And both Kp and Td are adjustable, means both are variable, Kp and Kd. Now, again, one term is there, derivative time. What is the derivative time? It is the time interval by which the rate action advances, the rate of the proportional control action. So if we are going to apply the ramp input, so this one is going to be advances by this one is TD. This is the proportional controller. This one is the PD one. And how to realize block diagram? Keep this is the proportional part. Derivative part means here only S is coming in the numerator, whereas in the integrator it is coming in the denominator. And you can simplify, you can get the loop transfer function, you can obtain the transfer function like this one is. Then in the transfer function here, you can compare. This one is because S square plus twice zeta omega ns and plus some additional term is there. So here you can see this zeta is a damping factor. This factor here, it is going to be in larger because of some benefit is there. Because of derivative one here, this factor damping, because damping here, so here it is defined zeta dash, and zeta dash is equal to zeta. Zeta is the original damping for the original system, and it is added with kd omega n by 2. So that means damping is going to be increased, and increased damping having other effect. Other effect means is there, once the damping is increased, it allows more increase of more gains. And as a result, indirectly, some weight can adjust the speed. So if we consider the kV, that kV is coming at limit s tends to 0, s into GSHS. kV is known to you. That is the 3 error coefficient, Kp, proportional, kV because of the ramp input, and K because of the acceleration input. So here parabolic input, here it is coming as Kp into omega 1 by twice zeta. So main feature, damping ratio improves and maximum overshoot reduces. Because if the overshoot is going to become larger, that will affect the stability. Rise time and settling times also reduces. Bandwidth increases. So the result of what is the effect of rise time and setting in the time domain parameters, the people are knowing what are the 6 number of parameters: delay time, rise time, settling time, peak overshoot, and a steady state error. A steady state error every time we are discussing here, that gives the idea about the accuracy, whereas rise times, this gives the idea about the response, transient response, and settling time about the steady state response. Larger the value of rise time will be there. So this one is sluggish will be the inversely proportional. Similarly for the settling time. So for a faster system, rise time must be smaller and settling time must be smaller. So again, bandwidth increases, gain margin, phase margin, and resonant peak improves. So major advantage is there. It increases the damping of the system, which we have already seen, zeta dash, that is equal to zeta plus something additional term. And hence, system becomes some more stable. It is not direct way. And percentage overshoot will be less, and hence system will become some more stable here. So settling time decreases, and hence response becomes faster. So if we have to consider in one point, we can consider the advantage of derivative is makes the system response faster. Either it is the transient response or it is a steady state response. Disadvantage, it does not care for offset directly. So though when we are adding integral to the proportional, that is going to eliminate the offset, but here it is not direct. It is not bothered about the offset. So that is the major disadvantage. This is the realization using the operational amplifier. Now come to the proportional plus derivative plus integral, combination of all the threes. So here it is defined like MT is equal to, this is available in all the books. A standard relationship is there. MT is Kp T plus Kp T dET by dt. This is the proportional part. This one is the derivative part, and this is the integral part is there. So if you take the Laplace transform and take the ratio, then transfer function of the PID controller is coming as Kp, and then Kp into Td, that is KDS, and Kp by Ti, that is Ki by S. So here constants are there, Kp, that is the proportional sensitivity or proportional gain. Td is the derivative time and Ti is the integral time. So when we are considering the responses for a unit ramp input is there. Then this is the proportional. This one is the PD controller and this one is the PID controller action is there. Now we can realize this one is PID controllers here. So this is RS, KD, KP in the parallel way. So that all will be added there. Then main features here there. So PI here because it is a combination of proportional plus derivative and plus integral. So here PD controller improves the transient part. Means transient response is going to become faster and damping is also going to, over damping is going to reduce. Whereas PI controller improves the steady state parts. So in this way, combination of PD and PI improves the overall system. So if we consider the advantages of the all individual are available here. Suppose gain increases, which was less in the proportional controller, which was alone. Offset, there was offset in the proportional controller, which is going to be reduced because of the induction of the integral controller. Hunting, there was the problem of the hunting when integral was used alone. This one is going to be improved, and response time means the system is going to faster as the settling time here less, for the settling time is going to become a smaller. So the system response will become a faster one. That means advantage of all the threes are available here. But this is the major drawback is there, because this is a combination of large number of components. So system becomes complex and costly, and some way it will become less stable, because this one larger number of components are there. So their effect will be there. And this is the diagram or by realization by using the operational amplifier. Now compare the responses of different individual controllers. So here we have considered here, this is the time in the time domain. And basically we are considering the output of different types of actuators, means different types of controllers. Individually, this is the response, because this is the set point or desired value. This line, dotted line, this is our desired value. We want that outputs of the controller must set around this one, whatever output may be. Then on the time domain, here TR1, TR2, TR3. So this one is TR1 is related with the D type. Another one is related with the P type. Another one is related with the D type. And these are the rise time. TR1 means rise time of the derivative, TR2 rise time of the proportional, TR3 rise time of the integral controller. So individually we can see the characteristics here. If it is a derivative controller is there, the response is going like this. And after that it is going to become, because it picks up the noise and divergent nature. So major drawback, because of this it is not going to use alone. But if we consider their response time, this response time is very small as compared to the other one. Whereas in the case of proportional controller, their response time, rise time here, we can consider time taken to rise from 0 to 100%. So that is the rise time. So this is TR2. So this rise time, here some correction may be there. Here corresponding to this point, you can consider TR1. Corresponding to this is TR1, not this point. And this is the point where it is reaching the 100%. This is the rise time of the proportional controller. But proportional controller, the major drawback, this is the actual output of the proportional controller. This is the desired and this is the actual. So always this difference, desired minus actual, is the offset. Always offset will be there. So that is the major drawback of, and this is not so faster as compared to the derivative one. And if you consider the integral one, it takes longer time to reach the final value. So that is TR3. And another drawback here, this response is moving upward, downwards. This is considered as searching the final value. And the technical word is hunting. So this is not going to stabilize. This is not going to reach around this value. Here in the proportional, this is going to reach this value, a stable value, but with the error. But this is not reaching. Means always it is moving here. This is not reaching the final value. So this part is the handy, which is the major drawback. Because of this, integral controller is not used, and because of this faster, this response, divergent response, again derivative not used. But if some error is tolerable, then only proportional can be used alone. So this is a comparison between the individuals. Now, if we compare the PD and PI, so here the PD is there because now we have already discussed that PD is not taking care of offset. So offset is there, but the response is faster. Whereas if we are going to use the PI, this PI is going to take care of the offset. It eliminates the offset, but this is not faster as compared. So whatever the rise time of individual derivative is there, that is available here in this case, same TR1. Now, when we combine the PID controllers, so benefit of all the three are same. We are getting the rise time of the derivative one. Because of the integral, again, this one is offset is going to be reduced. So all the benefits of three controllers are combined here. Now, in the tabular form, if we can consider advantage of different parameters of the PI controller. So suppose here KP, advantage adjustment of the controller output, limitations, we cannot increase up to too much value because this may cause instability. So up to certain level, it can be advantageous. Beyond that, we cannot. KI produces zero steady state error because integral action is there. A steady state error can be minimized, but slow dynamic response and instability. KD provides rapid system response, means the system response is going to be faster because of the KD, because as the rise time is going to be reduced there. But it is sensitive to noise and non-zero offset. So that is the major drawback here. Then again, comparison of gain responses of PI, PID. When we are going to increase in KP, a speed of response increases, a stability deteriorates, accuracy improves. Increasing KI, a speed decreases, a stability deteriorates, accuracy improves. But if we are going to change KD, a speed of response increases, this stability, something improves, but no impact on the accuracy. Then effect of parameters output, a PID controller with respect to the time domain parameters, here rise time. In the case of P controller decreases, PI controller decreases. In the case of PID, a minor decrease, then overshoot, increase, a minor decrease. Settling time, a small change, increase, a minor decrease. A steady state error decreases in the proportional
Sir,
controller.
only 1 minute left. Sorry, sir. For only 1 minute left after completion of the session. Please, sir, rejoin. And student, please rejoin after completion of the session. Okay.
So should I stop or continue?
Yes, sir. Within 1 minute, it will be completed. And then
Okay.
again join, sir.